Okay, so let's do the 1993 E&M FRQ number 3. Let's go over this one. Yeah, this one is confusing. And I don't like, this is not my favorite problem. I thought the first two were pretty cool, but this one, it's a little, well, the reason I don't like it is that it's confusing. And so, I mean, just the whole premise of the problem is a little bit confusing. So you might get something like that where you just have to fight your way through it if you can. And remember, you only got 15 minutes. So here's what we've got. We got a mass spectrometer constructed as shown in the diagram is to be used for determining the mass of singly ionized positively charged ions. Okay, so there's a uniform magnetic field of 0.2 teslas perpendicular to the page in the shaded region of the diagram. Now, unfortunately, when I made these copies, the shaded part didn't come across in the copies, so I just put shaded region means inside this box. So this whole thing, this whole box right here has a magnetic field, and it's perpendicular to the page, but they don't tell you if it's out of the page or into the page, so you're going to have to figure that out. A potential difference of 1,500 volts is applied across the parallel plate L and K, which are separated by a distance d equals 0.012 meters and which act as a velocity selector. So, all right. So in which direction relative to the coordinate system shown above at the right should the magnetic field point in order for positive ions to move along the path shown by the dashed line in the diagram above? So here's the dashed line, and they want to know, okay, if this thing's going to go on a straight line path through here, don't talk please. If it's going to go on a straight line path through here, what needs to be the direction of the magnetic field? So let me just kind of redraw this a little bit. Let's do it over here. So you've got this plate right here and this plate. I'm just going to draw it a little bit bigger. Now this is at 1,500 volts with respect to this. Now whenever you see this symbol right here, this just means, hey, this is connected to the ground, which really means it has an infinite source of charge and it has 0 volts. So we're going to say that this is 0 volts and this is 1,500 volts. Okay, and to go from 0, think about what you have to do to go from 0 volts to 1,500 volts. You have to work against an electric field. So what this is telling you is that the electric field in here has to point in this direction. So here's my E field. That's the direction it has to be in. Now, if you've got a positive, it says in the problem, for positive ions right here. It says positive ions. So here's an ion, and I'll just draw it as a little positive, and it's moving through here. It's got velocity like this. But while it's in this little tube right here, while it's in here, it has constant velocity. Now, if it has constant velocity, what does that mean has to be true about all the forces acting on that? Yeah, it has to cancel out. Now, therefore, here's what we know, and this is for A. We know that there's an electric force that's to the left, which means that there has to be an equal and opposite magnetic force to the right. Well, we know it's positively charged. We know what direction the force is, so we can use the right-hand rule now to figure out the direction of the magnetic field. So V cross B, and I'm going to twist this around a little bit so I don't break my wrist. Okay, But if the velocity is like this, V, and the force is like this, the magnetic field has to be down into the page. So it has to be into the page. Okay? Like that. There's my B field. Into the page. Okay? Any questions on that? Okay? Now, the reason why this is tricky is that, well, look, they give you this thing about a mass spectrometer, and that can and you look at this complicated diagram, and it can really intimidate you, you know. And when you only have 15 minutes, roughly, to figure out how to do this, that's hard. So this problem starts off being tricky and difficult, which means I don't like this problem. However, the first two problems were fairly straightforward, so that's good. If you get the first two problems, if you nail those, you got a 5, at least on that part of the test. So, but hey, this is doable. It's just tricky. All right, let's do part B. It says, should plate K have a positive or negative voltage polarity with respect to plate L? Well, if the electric field looks like this, then this has to have a positive charge. I mean, that's where electric fields start. Electric fields start at positive charge and end at negative charge, unless it's an induced field, you know, from Faraday's law. But if you just have a situation like this, the positive charge, so K has to be positive. So so K is positive. There's a positive charge. Okay, now for part C, it says, let me move this down here so you can see the whole problem. It says, calculate the magnitude of the electric field between the plates. Okay, well, if I look between the plates here, you know, delta V equals negative E dot ds. Do you remember that? I mean, that's the basic equation for a change in voltage. And I always like to start with the most basic stuff. Of course, the electric field in here is uniform, and so we don't really need the integral. So you can say that delta V is equal to negative, and the negative just describes, you know, if I work, if the work done by the electric is, if I move a positive test charge from here over to here, I'm going to lose voltage. That's what that negative sign means. I don't really need that negative sign. So that's going to be E. And what is delta S? Okay, well, that's the distance between the plates. I'll just call it D for right now. So the magnitude of the electric field, if you're doing the magnitude, you don't need that negative sign. So you have E equals delta V over D. And delta V is 1,500 volts. And the distance between the plates is 0.012 meters. And I don't have a calculator or the solution manual with me. So what's the answer to this? Does somebody have a calculator? Okay, so 1,500 divided by 0.012 times 10 to the 5?
Yes.
And volts per meter, or what other units can you use for electric field? Newtons per coulomb, yeah. I mean, this is a volt is a joule per coulomb, and you cancel out the meter from the joule and you get a newton. So it's newtons per coulomb or volts per meter, either way. So there's my answer for part C. Actually had to do a calculation. Now, by the way, look at part C, everybody. Everybody, look at part C in this problem. You did not need to do part A or B to do part C. All right? So don't give up on a problem. If you have time, one thing I see, and I know it's late at night when we take these practice tests. It's in the review sessions, and I know you're tired, and it's easy to give up on a problem and say, oh, I can't do this. And you just kind of like give up. Well, don't think that, okay, maybe you can't do A. But don't think that because you can't do A, you shouldn't do B or C. You should try every single part of every problem, because you might be able to figure out it might be totally independent of the others. So, just a few points makes a big difference. Now let's do part D. And it says, calculate the speed of the particle that can pass between the parallel plates without being deflected. Okay, so we want the speed of it. Well, what do we know? Let's go back to our sketch up here. We know the electric force has to be equal to the magnetic force in magnitude. So Q, we'll give this a little charge Q. Q times E, and look, we know what E is. So this one does depend on this, but you can at least set it up, even if you didn't get the answer for part C, is equal to the magnetic force, which is Q V cross B, but everything's perpendicular here, so I'm just going to do that. Now the charge cancels out, and so the velocity is going to be equal to the electric field divided by the magnetic field. And isn't that interesting that if you take the units for electric field and divide it by the units for magnetic field, you get meters per second? It turns out to be a really profound idea later on in physics. If not in this situation, but if you're talking about electromagnetic radiation, this E over B equals the speed of light, which is pretty cool. Yeah. All right. Now, but not in this case. So the electric field is 1.25 times 10 to the 5 volts per meter. And then this B is, I think they gave us that 0.2 Teslas. And so if you take that answer that we got before and divide it by 0.2, you get, 6.25 times 10 to the 6? Is that right? Or is it still 5?
Yeah.
Oh, 5, yeah. Meters per second, let me count. 1, 2, 3, yeah, 4, 5. And so there we go. Not too bad. Not too bad. And then part E. Let me, oops, I'm off the camera. Tell me if I'm off camera. Let's do part E over here, since there's room. It asks, it says, calculate the mass of a hypothetically singly charged ion that travels in a semicircle of radius r equals 0.5 meters. Well, once we get out here, you see, let's just draw a free body diagram of this guy. I'll just draw it on the drawing. I've already messed this test up. Well, it's moving now in a uniform circular motion. So you know that the magnetic force points towards the center of the circle. So the magnetic force is a centripetal force. So say, okay, F sub B is equal to mv squared over r. Okay, well, and this is QVB. Let's see. Oh, but we don't actually, Oh, we know the velocity and the radius. We don't really need to do it this way, because we know what the magnetic force is, or we can figure it out, right? Because the magnetic force equals the electric force. So M is going to be equal to the magnetic force times the radius divided by the velocity squared. And so, well, the magnetic force was just equal to the, we still need to know the charge. It says, oh, it's singly charged. Singly charged. So we do know what the charge is, right? Okay. So I can go back and use this. This is just going to be the electric force, which is Q times E. The solution manual probably didn't do it. You can use QVB if you want. And then times R over V squared. Now let's plug in our numbers, and the numbers here get quite long. This is 1.6 times 10 to the negative 19 coulombs, right? That's a singly charged, that's a charge on an electron. And then E would be 1.25 times 10 to the 5 volts per meter. And then R is given to be 0.5 meters. And then the velocity we calculated was 6.25 times 10 to the 5 meters per second. Now, by the way, what if you didn't get part D? If you set it up like this, or actually you go QVB, or whatever, you'll get most of the points. So, look, we talked about, earlier in the year, we talked about a freely moving charged particle in a magnetic field moving in circular motion, having a centripetal force moving in circular motion. So, looking at this drawing, you would have to recognize that and show that in this problem. And I'll leave it to you to figure out what is the mass. Does anybody have the solution manual? Just tell me. I don't want to.
56 times 10 to the negative 26.
Maybe somebody should check my arithmetic here. Oh, it should be. Yes, thank you. And now I kind of cheated and used this, but if you go QVB and then the V's will cancel, but it'll all work. All right, now finally, for part F, a doubly ionized positive charge of the same mass and velocity as the single charge ion enters the mass spectrometer. What is the radius of the path? Well, first of all, it's got twice the charge. It's going the same velocity and everything. So, first of all, its radius is going to be smaller. Now, is it going to be half because it has twice the charge? I don't know. Let's see. I don't really. So, I'm going to take this and let me just say, okay, the magnetic force is equal to QVB, but that's going to be equal to mv squared over r. And so if I solve for r here, r is going to be equal to mv squared over QVB. Is that right? Did I do that right?
Yeah.
Now, okay, velocity cancels that, but it doesn't really matter. Because what do they say is the same?
The mass and velocity.
Yeah, the mass is the same, the velocity is the same, the magnetic field is the same, but what are we doing to the charge? We're doubling the charge. So do I need to plug in numbers here? No. All I need to do is say, oh, I've doubled the charge, so this is going to be half as big. So the radius, instead of being 0.5 meters, the radius is going to be 0.25 meters. Is that correct? Check my work. Okay. So that one But hey, if you didn't see through that little logical puzzle, and you might not, because this is probably the last problem you're going to work on after taking the AP test, your brain's going to be pretty fuzzy. But, you know, just plug the numbers in. So let me zoom out and we'll take a look at this whole problem here. What? Well, okay, first of all, I'm explaining stuff. And secondly, you know, you're not going to finish the test probably.
I know, I didn't get really all this.
Yeah, so I don't expect you to finish the test, but I am explaining it as just as a, yeah, you can go. All right, so the problem is this part. I think A and B are the hardest questions on this test, on this problem, because it was very confusing. But notice that if you said, okay, well, this is 1500 volts, and this is 0 volts, C is pretty easy. And D is a little tricky, but E and F are very straightforward. If you remember that a freely moving charged particle moving in a magnetic field, that magnetic force is going to be a centripetal force. You need to know that, okay? You need to know that the magnetic force for a freely moving charged particle is a centripetal force. So you might see that. Okay, that is all.